Water is a critical resource in space, as it has a vast assortment of applications, ranging from its requirements for life support to its potential as rocket fuel. It has become evident that water will play a key role in the expansion of human exploration in space. However, transporting water to the moon is extremely expensive. As a reference, it costs about $100,000 to transport 1 gallon of water to space. As a result, there is a clear need to develop new infrastructure that will greatly reduce the transportation costs of water. Based on this motivation, Capstone Team 21 has been tasked with developing a conceptual design for a water storage facility that can operate on the surface of the moon. The water storage facility must be able to store 10,000 kilograms of water and then output this water as a liquid. It must also be able to function automatically and operate safely and reliably in lunar conditions. Lunar specifications include temperature ranges from 41 to 400 Kelvin, a 14 day and night cycle. Gravity on the moon is 16.6% of Earth's gravity, 1.62 meters per second squared, and it's also a hard vacuum. After thorough research and evaluation, the project team developed a final design that satisfies the requirements and specifications outlined in the problem statement. The final concept utilizes a storage tank containing 3 layers: a flexible polycarbonate inner wall which can expand and contract to accommodate both liquid and solid water storage, a foam glass 1 insulative layer used to minimize heat transfer caused by fluctuations in lunar temperatures, and a titanium cover which will protect the inner wall from external environmental hazards. The tank will be heated using a series of heating elements that regulate the water temperature using direct immersion heating. The heating elements will be installed on the inner ceiling of the storage tank and will provide an additional structural support to prevent the tank from collapsing upon itself. The water will be transported throughout the facility as a liquid through a flexible heated composite hose consisting of 4 components: an inner PTFE tube, a nichrome helical wire, and an outer protective titanium shell. Resistance power heating will be implemented through the helical wire, which will regulate the temperature of the water being transported. This design was chosen for its lightweight, high structural integrity, and adaptability to changes in the state of water. Numerous engineering calculations and analyses were required to complete the detailed design. One of the most challenging and complex design analyses was the thermal analysis. To manage the complex heat transfer systems with many changing parameters, the team developed a thermal simulation program on MATLAB to create a mesh object for the transfer line and storage vessel that imported various thermal material properties and defined different boundary conditions and initial conditions. The program then calculates temperature profiles using finite element analysis.
As shown, this was an example of the thermal simulation for the transfer line operation during the lunar day and during the lunar night for both initial system heating and normal operation.
This PNID can be used to analyze the process flow and highlight some key aspects that make this design unique. Before diving into the process, let's talk about some important design and operating conditions. The storage facility is designed to operate at a maximum pressure of 450 kilopascals, and the normal operating pressure is 350 kilopascals. The storage facility is designed to safely withstand temperatures ranging from 41.15 Kelvin to 405 Kelvin, and the normal operating temperature is 283 Kelvin. The minimum water level in the storage facility is 0.322 meters, which was analytically selected to prevent nitrogen from flowing through any of the water transfer lines. The maximum water level is 2.2 meters to prevent the system from overflowing with water. The storage facility is capable of storing a total water capacity of 11.27 meters cubed, which translates to 11,274 kilograms of water at our operating pressure and temperature. Now let's dive into the process. The very first step occurs when water arrives at the facility from an outside source at the water inlet point. At this point, water in the storage vessel is at the minimum level, which will be indicated by the load cell located beneath the storage vessel and its subsequent instrumentation control. Valves FCVO1 and FCVO2 will be opened, and pump P01 will transfer water to the storage vessel SB001. As water is transferred into the storage vessel, FCVO4 will be opened, and the nitrogen blanket gas will exit the storage vessel towards the nitrogen tank. Pressure safety valve PSVO2 will be set to 350 kilopascals and will ensure that the pressure in the storage vessel will remain at the desired operating pressure. Once the full load of water has entered the tank, the inlet valves FCVO2 and FCVO1 will be closed. The water will remain in the water storage vessel SB001 for the duration of the required storage period. The lunar conditions will likely cause the temperature and pressure in the storage vessel to fluctuate. Therefore, the compressor will be used in tandem with the heating elements to maintain the desired operating conditions. Note: water will be stored as a liquid for short-term storage, but during long-term storage, the heating systems can be turned off and water can be frozen and stored as a solid. When water is ready to be extracted from the facility, valve VCVO3 will be opened, and compressor CO1 will be turned on to push the water through the outlet transfer hose by a pressure differential of the blanket gas, and the water will be transported to the outlet point. Once stored water reaches the minimum level, outlet valve VCVO3 will be closed, completing the entire water storage cycle. The facility is now ready for another shipment of water. Now we will discuss some innovative design features of the storage facility. The water transfer lines and storage vessel are strategically designed with polymer materials that utilize mechanical properties that can elastically expand the expansion of water as it freezes. This means if a power failure were to occur and heat cannot be provided for the system, the facility can safely adapt to the expansion of water as it freezes, and then later return to its original shape. The storage facility is designed to utilize the ambient temperatures of the moon during a lunar day as a heat source for the water. This means that during operation within a lunar day, heat is transferred from the surroundings into the water, which significantly reduces the amount of energy required for the internal heating system. The compressor in the facility has a dual purpose of 1. Regulating the internal pressure of the system, and 2. Exporting water through the outlet line. This means that the compressor can be used instead of a second transfer pump, reducing the total mass of the storage facility. With this design, we here at Capstone Team 21 would like to help lead the charge in developing safe and reliable infrastructure on the moon for water storage. With this industry being in its infancy, there were several challenges and obstacles to overcome, which made finally completing this project incredibly fulfilling and meaningful. Finally, we would like to extend a huge thank you to all the support from Lunar Water Supply Company and the University of Calgary faculty and advisors for making this project possible.